Okay, so I'm making this video as a quick reteach of this lesson. It is supposed to supplement the section in your book, so that's where I want you to go first, is truly looking at the section in your book. But if you need some explanations out loud, that's what this video is for. So section 4.1 is about angles and their measurements. We have some definitions here, and I'm not going to spend too long on this screen. You can read all of the definitions. Two things I want to point out to you though is that S is arc length, and we're going to be given a formula to figure out what the arc length of a particular part of a circle is. So if this is our circle, then this section right here of the circumference is called an arc. So if we measure that, it's the arc length. That's some vocabulary for you. Additionally, we brought up the radian, which is a degree measurement. So we can measure angles in degrees or in radians. And radians is going to be something we use a lot more in trigonometry. So on this next screen, it just kind of helped us get the definition of a radian so that we understood the measurements along the coordinate plane. Basically, what we get at the very end is that if we go all the way around the circle, we have measured 2 pi radians. It has to do with the circumference of the circle. And if the entire entire circumference of the circle, so a full 360 degrees, is 2 pi, then that means halfway, this just semicircle from initial position to terminal position, is 180 degrees. And that fact right there is going to allow us to be able to do a lot of our conversions, because if 180 degrees is the same as the radian measurement pi, then we're able to use these degrees to radian measurements to change numbers from radians to degrees and degrees to radians. So if we were given 120 degrees and we wanted to know what that was in radians, we would multiply it by its scalar here of pi divided by 180. And then reduce the fractions, and then so 120 degrees is 2 pi over 3 radians. Now, something I want to point out to you now that I personally don't do an amazing job of, but I'm going to try to do better. Your book does an amazing job. When we're measuring in degrees, the degree symbol has to be there. If there's no degree symbol, you're measuring in radians. So even if it's just a regular number without a pi in it, if there isn't a degree symbol there, you're measuring in radians. So make sure you use your unit there of degrees or radians. You can kind of see how this works. If you notice on this side, I'm using some shortcuts to be able to do this math in my head. If something is on both the numerator and denominator, they cancel each other out. Numerator and denominator cancel each other out. So if it is easier for you to not turn to a calculator and do these in your head, make the numbers easier for you, just throwing it back to some of the things that we learned about dividing back in elementary school. Okay, so here we get to that arc length formula. Remember, S is arc length. So arc length is equal to the radius of the circle times theta. Now be sure you notice this is measuring in radians. So if you're given a degree measurement, you'd either have to transform that degree measurement into radians or use the formula on the next slide, which we'll get to in a second. I made this connection in one of the classes to those of you who are in physics. You may have learned distance, rate, and time in this little triangle. So distance is equal to the rate times the time. And you can very quickly solve for whichever variable you need and or want. So this formula as well, S equal to R times theta, kind of works the same there. And if you don't know what I'm talking about, then just use the formula as per usual. In this particular problem, we wanted to know how much longer lane 2 is than lane 1 around one turn. One turn on a track is pi radians. So the angle measurement around one edge of a track is pi, 180 degrees. But we're measuring in radians, so that's pi. So we were able to compare the two arc length for lane 1, arc length for lane 2, and see that their distance or the difference between them is about pi, or about 3.14 meters, which if you actually looked at a track is why they have a staggered start on the curves, and they're all about 3.14 meters from each other, which I think is pretty cool. Now, last but not least, we have our arc length measurement in degrees. So we have derived a formula here, arc length equal to pi times the radius times theta, all divided by 180. That actually converts the degree measurement into radians at the same time. So you can either remember to use this formula if you're given a degree measurement, or you can just convert the degrees to radians, which is it's what this formula is doing anyway, since that conversion factor is in there. But in this particular problem, we wanted to find the perimeter of a 60-degree slice of a large pizza. Okay, so we want the perimeter. That's all of the outside. So I need one of the sides, another side, and the arc length. Okay, well, the sides of this pizza, when it's cut correctly, the way, you cut around pizza through the center, both of the sides should be the radius. So this is 7 inches and that's 7 inches. Great. All I need is the arc length here to know how much my crust is, what the perimeter of my crust is. So I fill in the formula. Pi is a constant, so it stays. The radius is 7. The degree measurement is 60 degrees, all divided by 180. Bloop, 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 bloop. We'd get 7.3 inches. Okay, so the perimeter, 7 plus 7 plus 7.3 is 21.3 inches. So if you were wondering what the perimeter of your slice of pizza was, and you could get a ruler out and figure out the radius, you would need to know how much the curved part of the pizza is, which is your arc length. And now I have a way to do that, in case you're wondering. Now the last example here is all about conversion. So it's converting one measurement into something we know, specifically going from revolutions per minute to miles per hour. So this is what the computers in cars are doing when they're measuring the tire's diameter and the circumference of the tire to get it translated into miles per hour. Like that's what your dashboard is doing whenever you're measuring your speed versus your revolutions per minute. So a couple things we needed to know, just because I know you're going to need this. There's 5,280 feet in 1 mile. Just a conversion factor we're going to need. We also know that this guy's truck is 36 inches in diameter. Now, if 36 inches is my diameter, that means my radius is half of that, so 18 inches. Which means that for this particular circle, a radian, which is related to the radius, is 18 inches. So 1 radian, 18 inches. That's good to know. All right, so we start with what we know. We knew we had 630 revolutions per minute. When you're doing conversions, unit conversions, you need what am I trying to say? The unit that you're trying to get rid of needs to be on opposite sides of the fraction. So we're trying to get from revolutions per minute eventually down to miles per hour. Okay, we have to be creative in how we do this. So one of the conversions I know to get from minutes to hours, well, I have a minute to hour conversion. There's 60 minutes in 1 hour. 60 minutes has to go up here so the minutes cancel. And then they do. I could go ahead and simplify this if I wanted, but I'm going to wait till I have all of my conversions done to just multiply one time. The next thing I know, we just learned this about circles, is that circles have a revolution degree measurement, 360 degrees or 2 pi radians. So now my revolutions will cancel and I'm left with the units of radians per hour. That's not what I want yet, so I'm going to keep going. For this particular wheel, it has a relationship between radians and inches. And it has everything to do with that radius. So there is 18 inches in 1 radian, making sure the radians cancel. So at this point, we're at inches per hour. But I want miles per hour. So let's get out of inches. Let's get to feet. So to get rid of inches, there's 12 inches in 1 foot. Well, the inches will cancel. Now I'm at feet per hour. And then I can go from feet to miles. Again, the feets need to cancel so that I have miles per hour. All that's left to do after that is to multiply all of the numbers. I didn't highlight the ones because you can multiply by 1, but it doesn't change anything. So I multiply all of the numbers in the top and the bottom and actually do this math here to finish the conversions. And if you're rotating at 630 revolutions per minute, that's 67.47 miles per hour, which is just cool because that's what the computers in your car are doing. Is this trigonometry math to go from angular and linear motion to angular speed. I think it's just cool. I know that was fast and furious, but again, it is just supplemented to the book if you needed to hear this out loud. Yeah, have a good day.